Welcome, everybody. Thank you, Cesar. Again, Cesar Rodriguez, AMBER colleague, managing Rios Convida from Spain and doing great work for rivers and making great music for us as well. Thank you very much. So we are now at the 4th sessions of our summer camp, the AMBER summer camp. AMBER stands for Adaptive Management of Barriers in European Rivers. And we are at the end of the AMBER project after 4 years and now sharing results. And in these sessions of the summer camp, we want to give more insight into the details and efforts being done on our work of the last few years. So it's more like a workshop, you could say. So we very much promote that people ask questions. You are in a view and listen only mode at the moment. When you're watching, you can ask questions via the Q&A buttons there at the bottom of your screen. You can share ideas or links that you want via the chat function. If you want to speak up and be present also in as a panelist, then please raise your hand and we can get you in if you want. And so as mentioned, we are now in this is the 4th session of the summer camp program, looking at telemetry. I'm not sure if that's the right way of pronouncing it in English. But anyway, my name, by the way, is Arjan Berghuizen, working for the AMBER project on the communication part of it. And today we will be listening to Martin Lucas, who is very experienced on this issue, author of many books on fish migration and other issues, and he's the right person, I think, to talk about telemetry. Martin, can I please ask you to share lessons learned and ideas that we have from the AMBER study of the last 4 years regarding telemetry?
Thanks, Arjan. Okay, so yeah, most of the other sessions have been slightly shorter, and I'm sort of acting almost talking for 2 people, so we'll have a slightly longer set of slides here. Hopefully you won't all fall asleep staring at the camera, but if you do, well, we'll wake you up with some gentle music later on. So I'm going to talk about telemetry for rapid barrier assessment. And I'm mostly going to be talking about pit telemetry in that regard, and about how to go about doing it. As might become apparent later on, actually, in most telemetry, including pit, it depends what you define as rapid, but pit is rapid relative to most other forms of telemetry. So you can see on this image, you've got this telemetry line and antenna going across this channel here, and I guess I'll be picking up on that on a few occasions as we go through. So some of you might have seen this slide before that Christian Walter showed the other day, and I'm just reinforcing that I'm only talking about impoundment structures as movement barriers here today. I'm not dealing with issues of habitat loss or anything. It's about assessing the degree to which fish can pass that barrier. Mostly we will be thinking about migratory fish, but of course in terms of connectivity and barriers, barriers are as important in terms of impeding dispersal as they are for migratory fish. So probably, if anything, dispersal is actually even more important to us in terms of removing those barriers. And yet most of our work worldwide on movement past those barriers is in terms of migration. So this figure here just gives you an idea of the ways by which movement within rivers is important for fish in terms of seasonal movements, in terms of life history movements. And if we want diverse rivers, in terms of communities, we've got to facilitate these kinds of movements. And this in many respects for spatial ecologists of fish, dealing with damaged rivers, non-flowing rivers, barrier-ridden rivers is the holy grail. achieving high natural biodiversity in flowing, non-degraded rivers. It's not easy, as that's why we've all been doing this. It takes time to get there. And Alex Harrow and Ted Castro-Santos came across or emphasized this sort of phrase of transparent barriers, which sounds weird at first. Their idea is, even though we can't get rid of all barriers, we need to try and minimize the degree of impact on fishes and other organisms. In other words, make them transparent in terms of movements when we're using mitigations like fishways. And if we can do that effectively, the idea is we should end up with nice diverse communities like this one here in this Ray Troll mural. Of course, one of the best ways of making barriers fully transparent would be to do this kind of thing to them. So this is for the Embury Dam. Most dam removals, of course, are not this kind of visually conspicuous. And on many occasions, we're dealing with modifications of barriers that reduce their impacts and make them slightly more transparent. In order to do that, we've got to make assessments of those barriers. And this is one of the aspects that you've already heard about earlier this week in terms of rapid assessment of barrier passability. Things like the ICE method or sniffer or fish crossing or even the AMBER barrier assessment tool, which is kind of based on ICE method. But you can see for all of these examples here, this large estuarine barrage, large valley dam, they're going to be difficult to do that kind of assessment on. It's not going to be a rapid assessment, whereas making rapid assessments of passability is going to be easier for small barriers. And as we know, small barriers are by far the most abundant of all the river barriers, certainly across North America, Europe, etc. And it so turns out to be the case that actually using telemetry as a rapid barrier assessment tool is a lot easier and faster on small barriers as well. And although big barriers are important for their impact, it's often the small barriers that we can more readily mitigate, reduce the impacts of, remove. So actually getting that kind of barrier information is important. And yet the weird thing is about those kind of conventional barrier assessment methods, those rapid methods like ICE and sniffer, is that a large proportion of these small barriers come out as partially passable, partially permeable, but we don't know really to what degree they are. And so telemetry is one way of actually giving more concrete information on that. Also, telemetry can give quantitative evidence on passability that, if it's relatively low, can then be used to leverage funds, or leverage, if you're American, leverage funds for perhaps removing that barrier or doing something about it. Quantitative evidence can be important. So in that regard, then, telemetry becomes the gold standard for assessing the passability of barriers for fish, because it enables individual identification of fish. In particular, I'm talking about use with electronic tags here, although telemetry generally can be used to refer to kind of gathering information remotely at a distance. It can be used to include things like Didson and Aris, those kinds of photographic style sonar. But the key thing about individual identification with telemetry tags, you can measure the number of successes by individuals divided by the number of attempts. It gives you a good metric of how readily passable a structure is. You can quantify the number of approaches to the structure, the number of entries to a fishway at the structure or onto the structure itself. You can quantify the number of individuals that manage to pass, or those that fall back over the barrier. And so you can easily calculate percentages of approach, entry, successful passage. You can also measure the route taken. There may be 2 or 3 routes past a particular barrier, and that's important to be able to do that. And you can measure the time taken for the fish to pass, and that's important because if they're aggregating, they will be potentially susceptible to exploitation by fishermen or by predators. So they're both issues that we need to kind of solve. And you can see from this image here, a whole bunch of the different types of telemetry tags used. And in this image here, I'm showing, just a range of pit tags in particular that I'm emphasizing. But the question is, given that it costs time and money to do telemetry compared to perhaps one person or 2 people taking a camera to a site and some measuring tools, perhaps a flow meter, and making an assessment rapidly of passage of something in a crude way, is this telemetry method using a sledgehammer to crack a nut? And the degree to which we answer that would be, yeah, it is to a degree, but it gives us crucial information that can be gathered in no other way. So we wouldn't want to do it at every site, but some key sites it can give us representative information from, by which we can try and extrapolate to other sites. Certainly it can give us, as I say, quantitative information that can be used as evidence. The other thing about telemetry, of course, is it relies upon the fish doing what it should if it was untagged. So if we're going to capture fish, tag them, put them back, we've got to be able to have good reason to believe there's no impact on their behavior or their performance. And if we're not sure, then we need to be able to measure that. Often licenses or ethical permissions are needed for any of this kinds of work. So we need to get that. Many telemetry studies take months, some take years. That is not rapid by most people's thinking. So again, there's the context of how rapid is rapid. But it's certainly true that in rivers, the quickest, cheapest, most flexible option for assessing passage past structures is going to be pit telemetry. And so that's what I'm going to spend the vast majority of my time talking about. And there are a bunch of good publications out there that you can get information on how to do that. But I'm going to give you some kind of clues, hopefully. But before I do that, the first question you probably always want to ask yourself is, sure, it's fun tracking fish and seeing what they do, but is telemetry the right method for assessing the impact of a barrier? Is there an easier way of doing it? And this gives you one example of where actually it's quite handy. So this is a barrier before removement, and just using telemetry, using electric fishing, standard surveying on a small river down at the bottom, down at site 1, to actually measure what the abundance of, in this case, eels was. So at site 1, downstream of this barrier, so down here, eels were abundant in 2 seasons, autumn and spring, before this barrier was removed. Whereas upstream, in 5 different sites upstream, all combined, negligible number of eels, especially the small young recruits, were present. And yet after that barrier was removed, then they rapidly colonized. So you have to make an inference, but there's good evidence here from quite quick and dirty surveying, but at key points, that the barrier was acting as a barrier to eel passage. Here's another example on a slightly bigger tributary of the River Wear in northeast England, where you've got a whole bunch of barriers along this tributary. This is the main river here. This is the tributary coming off the side here. And again, electric fishing has been done on that river. We've measured the actual density of those fish. And these just represent the densities of different species and increasing distance going upstream here. So these are the various sites going upstream. And you can see that although there's a bunch of species present right at the bottom, below the lowermost barrier, by the time you get to past the second barrier, actually you've only got 3 spiny stickleback, eel and brown trout available. Most of those, the dispersal, it could be inferred, as dramatically being reduced in this river, which in this stream that was once formerly polluted. It's now much cleaner, but the recolonisation of that has been dramatically inhibited by all these very small barriers in this case. Again, we've inferred that without using telemetry. But if you're going to do that, you need to make sure you use sensible sites. And here's an example, another stream on the River Wear, on the northeast of England. This small stream here, salmon spawn in it now, trout, the eel are in it, a range of species, but it's got all of these small barriers. The main river's got a number of large barriers, but they've all got fishways on them. So there's a degree of passage mitigation. No types of mitigation in this river at all. No barriers been removed, no fish passes put in. And actually, if you look at the fish communities in it, in most of these areas up here, they're very denuded, very depauperate fish communities. And yet the national agency that's responsible for surveying the quality of these fish communities and trying to largely oversee rehabilitation, and it has a single monitoring site down here, downstream of every single one of these dispersal barriers. And their assessment comes up with a good fish community score. There are young salmon there, so they say, actually, there's no problem in this stream river. Therefore, our computer predictive model says no point in trying to remove barriers on that because it's good already. Duh, as Homer would say. Therefore, if you're going to use this sort of method, make sure you pick the right types of sites in which to do those assessments. So yeah, I'll probably get some rude emails about that from our national agency later on today. Hey, that's life. So do you still want to do telemetry? If you do, then you've got to make sure you've got the relevant legislative cover. So if you need a license in that country or region, you need to get it. You need experience, which you can get perhaps from various workshops, collaboration, etc. If you haven't got a license or enough experience, then collaborate with those who have, because usually they're only too willing to do so. Be aware that the requirements can vary regionally and nationally, and you usually have to put a project idea through an institutional care and animal use committee. And of course, have you got the funds? Because telemetry tends to be moderately expensive, and there's no point in doing such a study poorly with, for example, tagging insufficient fish. So if you haven't, then again, think about collaborating with groups who might have the equipment, or there might be central equipment pools that would loan you the gear, but you're not going to be popular if you damage that equipment. So be aware of what equipment you need. Buying equipment and then not using, or buying the wrong equipment is a really bad and expensive mistake. And just to make life complicated, here's an adaptive radiation, a kind of a sort of a classification of the methods of studying fish spatial behavior. And the ones we're interested in down in this corner, electronic tags. And even for that subset down there, there's a wide range of methods, and PIT is just one of those methods here, PIT, passive tags. So these ones that aren't actually powered by battery. And to make life more complicated still, and I will make this available actually as a PDF later on, because I appreciate, you know, these are everybody's worst nightmare looking at complicated tables like this. But PIT telemetry has a time and a place, is useless to a large degree in open marine environments, often in lake environments, where it really comes into its own, are relatively narrow, constrained habitats. So streams and small rivers, and especially things like fish passes and barriers, pit telemetry can be ideal because you can tag very large numbers of fish at very low cost, but it has a small range, and that's its major limitation. But also the tags are theoretically of infinite life. So long as they're not broken, you know, they can easily last 10 or 20 years in a fish. And you can tag fish as small as 5 centimeters with these. So you can tag very small species, you can tag very young individuals, and you can get to near to the point of tagging all of the members, all of the species and life stages present within a fish community. No other telemetry method has that capacity. Most studies with radioacoustic telemetry tend to concentrate on just 1 or 2 target species. And that's a problem because far too much stuff assessing barriers in aquatic science is done on just too few species. Trout, salmon, eel, you know, yes, they may be important target species, but we know far too little about the others. There's far too much bias. And pit telemetry, sometimes known as RFID, radio frequency identification telemetry, can help us solve that. So what is it? So passive integrated transponders, or PITs, basically they're a tag that have an integrated circuit in which gives them their ID code, no battery, and they rely on being energized externally in order to transmit their code back to the reader, as it's known. The reader is actually a transceiver. It transmits in order to interrogate the tag, and then it receives. So it's a transceiver. And they tend to, the radio frequency gear, but typically working at rather low frequencies. Whereas if you did radio tracking with a battery-powered transmitting tag, typically that would usually be VHF, very high frequency. And if you did satellite tagging or GPS tagging, they're typically using higher frequency still, sort of ultra high frequency. So you can buy your tags, you can make your own transceivers or readers and antennas from basic components, but most people buy these days. There are a variety of companies. I just picked 2 of the most well-known ones here, but there are others around the world, from within Europe and in Asia and in Australasia. Tags are cheap, and that's the big advantage, because if you've got a radio tag or an acoustic tag, might be, I don't know, a couple of $100 US. Whereas for that amount to tag one individual, you could perhaps tag, you know, 100 fish. So bigger sample sizes become possible with PIT, and that can be important. You need a hand reader in order to actually record what your tags are at the start, but then you need your field detection gear, usually at set individual sites, such as this, at a barrier here, where you're going to have a reader and perhaps with several antennas, picking up the fish as they approach, the tagged fishes, that is, as they approach and go past. And then you need a bunch of consumables in order to set that gear up. And the basic principles are that the gear is going to be powered by DC, usually 12 to 20 to 18 volts, something like that. Typically 12 volts off something like a heavy duty deep cycle battery, sometimes a series of them in parallel to give you a greater capacity, often supported as well in countries that get plenty of sunlight by UV panels that can also boost it. You can use mains power supply as well, but one key thing about pit telemetry is it's really sensitive to electrical noise, and mains power carries a lot of electrical noise. So you'll have to put that through a transformer and use the mains to trickle charge a battery that then feeds into the pit readers. Otherwise, you'll never actually be able to detect anything. You won't be able to tune your antennas. And a crucial part of that, here's a hint, you need to use generally linear transformers or similar things, like the old style heavy ones with a big coil, which basically soaks up extraneous frequency from AC power generation. So your power, and then your battery supply, and then your reader, and then that sends the signals out through a tuning module, which actually ramps up the voltage and creates an induction loop. And when the pit tag enters the magnetic field created by that induction loop, it actually is energized and it returns its identification signal. And different types of antennas in terms of the size and the need for us will be formed from different types of antenna wire. So some of them with many, many fine strands and big, thick loops are going to typically, big, thick wire are going to be used on the very biggest antennas, and they'll need greatest amount of power to actually supply them. So here's a few things to watch out for when you're setting up this kind of kit. Sites near electricity pylons suffer a large amount of stray radio frequency noise. You know, if you ever have been traveling in a car and kind of you've got your radio on, you know, on a sort of AM frequency, you'll often hear a lot of static hiss as you pass under kind of electricity transporting pylons. And that's basically the sort of noise that your pit receivers also suffer in that environment. So, you know, here's a weir here. If you've got great pylons nearby, you're unlikely to be able to set up a pit telemetry station. So don't bother trying that. Or if you do, make sure you test very thoroughly before. Sometimes you can get away with it, sometimes you can't, but it's something to be aware of. Also, be aware that although the supply to pit telemetry will be 12 volts, by the time you've got the electricity running through the tuned antenna, through the tuning box and into the antenna, the output of that may well have been ramped up beyond 200 or 300 volts, but it's usually of a low current. So it's fairly high voltage, but low current. But you should be careful. You can get a significant shock off that. And, you know, if you've got people trying to take a metal knife to it, Stanley knife or metal pliers, because they just want to, I don't know, steal your cables or whatever, they could get a zap as well. So safety first and be careful. Another thing is, if you've actually got a cable running from one bank to another and then across the bed, you need to be careful. If there are kayakers going down there and you've suddenly put up pit gear overnight, you do not want to garrote those people, or for them to suddenly be caught by your pit gear and risk being caught underwater. So you need to be careful if there are boaters on there. And if there are large boats and you're trying to use what we term a swim-through antenna, that may just trash your gear. So there are circumstances where you can't use it. And in urban environments as well, be careful of vandals. Some of our gear before now, people just tried to steal the antennas just because of the large amount of copper wire that they saw there, or just for being vindictive. They'll throw batteries in the river or steal the batteries and sell them on. Unfortunately, it seems the UK suffers worse for that than some other countries. But just, if need be, put a dummy station out for a few days before you put your real station out. Just check whether or not anybody's going to cause any hassle to it. And perhaps working with local people, sometimes if they're informed, then, you know, that can work. Two main types of pit telemetry: half duplex versus full duplex. They have their advantages and their disadvantages. Basically, half duplex requires the reader to transmit and then to receive. It can't do both simultaneously, whereas full duplex can. And because of those different modes, half-duplex actually reads tags in a different way to full duplex. So in half-duplex, after energizing the tag is read at the same, typically at the on a different frequency. Typically, there's certainly two distinct periods. Whereas in Fdx, there's an amplitude shift on the same frequency, and the implications of that are generally that with HDX you get slightly better range, or markedly better range actually, because they're less sensitive to noise, to radio noise. Whereas with full duplex, there's more of a high-tech demand because they're more susceptible to radio noise. You have to have more carefully tuned antennas, they're more sensitive to vibration, you tend to get a lower range from them as well. But because HDX tags have to have a capacitor in the tag store energy before then transponding, that makes the tags bigger than Fdx tags. So the very smallest tags are always Fdx tags. But basically what we want to use for rapid barrier passage assessment is HDX. Those kits are much more flexible for building the antenna that you want in a matter of hours for the right kind of place in the field. You also need to choose the right pit tag for your study. All of the tags have got copper windings in. This is what receives the signal and transmits it, and through that induction. The very smallest tags can be injected. Usually the bigger tags will be inserted after very minor surgery, just making a very small incision with a scalpel and inserting the tag, usually into the body cavity, sometimes with the smaller tags into musculature. There are advantages and disadvantages of both of those methods, but basically you want the tag to be retained for life by the fish, and there are advantages and disadvantages to those. The smallest tags may only have 10 centimeters range or so. The biggest tags can have more than a meter range from the antenna if in the optimal direction, and this just shows the range of sizes. The biggest tags are kind of 30 millimeters long, and the smallest are about 6 millimeters long. If we actually think about HDX types of antenna design, the most commonly used one is a swim-through antenna. So this is basically the channel in terms of its cross-sectional area, and the tag, the fish you would imagine would be swimming upstream or downstream. The tag will be inserted into it in such a way that it is longitudinally positioned parallel with the course of the river, and so as the fish swims through the antenna, it gives the longest read range and hopefully reliable detection. But you can also have swim over flatbeds where the tag is actually at non-ideal orientation, and this gives a lower read range. You can have it set up perhaps around a cylinder, for example in a culvert or a pipe, or you can attach an antenna, for example, on one side of a bridge wall. So provide the fish swims closely, then you may pick it up. Here's just an image just showing one of these setups. Here you've got antenna wires actually unprotected here. This is perhaps not advisable, but it's a quick setup. You would not want to set it up like this if there was a risk of canoeists coming down and garrotting themselves. Equally, it's better to protect these where possible because it makes them less susceptible to damage by large woody debris, etc. And this just gives an indication, a schematic of how the antenna would be set up there. So these kinds of things you can set very quickly to whatever the form of the river is. You couldn't do this easily with an FDX array. It would be too sensitive. You couldn't set out flexibly. There would be too much vibration or movement of the antenna over time. You just couldn't get away with it. You need to allow for rising water levels. So you can see these are higher than the water level, so that if the water rises with higher flows following rainfall, then you've still got the whole channel being interrogated by the antenna. So site choice is important. You typically want quite vertical banks and then a relatively flat bottom in order to set these up quite nicely. These show some examples of more high-tech antennas. Here's an Fdx antenna pre-built in a factory. You often actually covered in epoxy, so the antenna's pre-tuned. It cannot alter its position. It's nicely protected, and it's here positioned robustly. Here's a whole bunch of Fdx antennas all next to one another on a particular river site, and these are all operating. These are all actually synchronized together off a single system. Here's 3 different flatbed antennas actually together interrogating the full width of a stream. Here's one antenna, HDX, I think, around a vertical slot entrance in a fish pass. You can have every pool of a vertical slot having one of these, so you can detect the fish moving from pool to pool. Here's an enormous HDX antenna being built. Here's FDX antennas. You can't see them, they're further up here, but they're linked to a tube. This is on the Columbia River, a tube where actually that part of the tube actually has a hinge in it, and it's air actuated so it can open in response to a signal. And the antennas are linked to a database containing millions, certainly hundreds of thousands of fish pit IDs. And in the time scale that a fish goes down through those pits that are just a matter of tens of meters further away, the air actuated opening can drop the fish out into a bypass system for scientists to pick up in the time scale that it interrogates the whole of that database. So incredibly fancy systems. Clearly that is not a rapid assessment tool of any description. Designing HDX antennas. Everything you want to know in the time that I haven't got to tell you is available on this handout. It's a really first class antenna handout. And Oregon RFID do a range of kind of training courses. Other groups do as well. There are others other than just Oregon RFID, but that's a really high quality resource that tells you step by step what you need to know about building and tuning antennas. But basically, when you build an antenna, you need to actually alter the inductance of it in order to tune it. And the choice of that antenna, its size, and the number of turns you put it is dictated partly by the choice of the wire you use, but also the size of the antenna and the shape. So if you're doing something like a swim through antenna, it depends whether it's small, for example, I don't know, 1 meter by 1 meter in a fishway, or if it's a whole river channel width before a barrier or after a barrier, where it might be, say, 15 meters wide by, I don't know, 1 meter deep. Those differences will dramatically influence how many turns you choose to make in it and how the thickness of the wire and the stranding of it. So you can make predictions that you can measure with inductance meters like this, and you can calculate the number of wire turns needed and actually space between individual turns. And they're influenced by things like proximity to metal. In general, metal near your antenna is a bad idea, but sometimes it's unavoidable. So once you set up that antenna in the field, you then have to tune it to a resonant or close to resonance to give the best range, essentially. And if it's well set up, then you'll get a good range. You won't use up too much power, and also you won't risk burning out particular circuits. It is feasible to burn out circuits if you're pumping too much power into to the antenna and you don't want that either. So basically you change a series of jumper settings which alter the inductance. So you change jumper settings of a series of capacitors within the tuning box that alter the impedance of the antenna and hence alter its magnetic induction. And there are various tools that can help you do this, from changing these to fine tuning, but you can also get automated readers as well. And usually they're really helpful, but there can be circumstances actually where they're unhelpful. If you want to detune so that a fish has to be close to the antenna, then these kinds of automated tuners make life really difficult. And a good reason why you may want to detune is to reduce the chance of what we call sitter fish causing frequent detections. So if a sitter is moving up towards a weir but not passing and sitting near the antenna, you may just fill a data log or will data from that fish. You don't want to do that. So there can be reasons why you might change that. Tag orientation is crucial in terms of how well your antenna will work. And theoretically, you would tend to build swim-through antennas if you can, because in most cases, the tag will be in close to a more optimum alignment as it approaches perpendicular to that antenna. Whereas if you have a swim-over antenna, then the tag will typically be above it and give you a low read range. So if your fish swam high in the water column over a flatbed, there's a high risk you will not detect it. So flatbeds can work well in shallow water, but they do not work at all well in deep water. Then you'd be better off with a swim-through antenna or a modification of those. And these images here show the difference, the field pattern that you get with tags in relation to its orientation. You need to do tests of that around your antenna in order to work out how well you can do that. And you may need to modify your antenna design according to the particular setup. If you've got a shallow, relatively narrow stream, say 10 meters wide by ½ meter deep, you can just use a simple single loop antenna usually will be appropriate without a hole in the middle. If you get poor range, often results in a hole forming in the middle of the antenna. When I say a hole, I mean a detection hole where you get zero range, and if the fish passes through that, you don't detect it. But as you increase the depth and or the width of the channel or the area you're trying to interrogate, the chances of such a detection hole appearing increase, and you have to do things to reduce that. So one way by which you can do that is do a figure of 8. So you start from this side, you go down, up, across, in this particular situation, then down, and then across, and then you would reverse the route of that on the way back. So that's one way, a figure of 8 design, and that needs some supporting elements within the channel. So these typically would be, for example, wooden stakes driven into the bed of the river, which is fine if it's sediment, but not if it's bedrock. You may have to try and pile in, you know, steel, and then you'll probably struggle to tune your antenna. So these are the kinds of issues you have to deal with. But also deep channels, if you've got, for example, a deep opening to a barrier, like a massive fish pass opening, that's, or a navigation lock, for example, say it's 8 meters wide but 3 meters deep, you can, by careful winding in an appropriate direction, like shown in Vince Tranquilli's view here, you can actually tune that. But it's important that the antenna can't flex too much. You can do these, both of these quite easily with HDX systems. They're much more difficult with FDX. Not saying not impossible, but in terms of rapid provision in a channel, much more difficult with FDX. One of the big problems, again, with these kinds of things is debris build-up on swim-through antennas. And this is especially the case in spate streams, in wooded catchments, where if high flow brings woody debris down, and the extra strain on that then actually causes loss of the antenna. Or worse, it may cause complete damage to all your pit kit, and you lose data as well. And one of the problems is that high flows are when a lot of fish migrate, and you lose data during that period. It means you have no real idea of how many fish were attempting to pass your barrier and how many did. So one of the problems with pit telemetry is ensuring continuous data capture despite variable environmental conditions. Here's an example shown by Finley, this kind of breakaway antenna solution where you have low strain breakaway releases here that enable the thing to actually break away and not cause damage or loss of the whole equipment, but also the pit loop itself can actually break away here using this connector here, and then when the flows have decreased you reconnect it. It doesn't actually solve the problem that you lose the data during that period, and so actually having a really robust pit system that can cope with high flows and debris build-up actually is arguably more advantageous than this. But those are problems for everyone. A slight alternative is a hinged buoyant antenna anchored to the bed, and which actually sits obliquely during elevated flows and tends to get swept flat by the higher flows and are less susceptible to debris impacts and damage. Multiplex systems are really useful because the chances are you're going to need to know the direction the fish is moving. You want to know how many approach a barrier, for example, moving upstream, how many get past the barriers. That means you need two antennas minimum, but often you'll want something like 4. One to detect fish approaching perhaps 30 meters downstream of the barrier, so that haven't yet experienced barrier attributes. They're arriving naively, for want of a better word. Then they're actually detecting the barrier itself and they're attempting to get over it. And then they're exiting the barrier upstream if they've been successful. And then perhaps you have another 20 or 30 meters upstream so that any fish that perhaps return back downstream can be undetected. So that might need 4 antennas. You can use a multiplex system that can read up to 4 antennas per reader and use one power source for all of those antennas, dividing the scans sequentially between different antennas. The downside of that is that each antenna is interrogated less frequently. So let's say you had 3 antennas, and roughly speaking, you had a total of 12 scans per second. If you do 3 antennas off that instead of 1, then those will be scanned perhaps every 4 seconds, whereas 1 could be scanned every 12 times a second. So there's an increased risk of missing fish that swim through quickly, especially if they're headed downstream with that kind of system. An alternative to that is multiple readers, where each reader perhaps has 1 or just 2 antennas per reader, but and therefore you don't suffer that problem less, but you need more power, and it becomes crucial to synchronize those readers together in terms of the timing of transmission and read, especially for HDX, because, as is shown here, you'll get large amounts of noise on the system and you'll fail to be able to tune each individual antenna and to record data reliably from it. So those systems are a bit more complicated. Tag collision is a problem as well, because if multiple tags are within the range of antenna, only going to detect one tag at a time, and that's normally the tag that's nearest it or closest, the single tag that will be detected. So if you've got a sitter fish right on top of the antenna, you will miss many other tagged fish going past, and this is a problem with pit telemetry. So you have to put your antennas in such a way that you try and minimize the probability of getting sitter fish, there are ways that you can say you can discount sitter tags from a recording system. So if a tag is continuously recorded, you can then tell the system to omit that until a different tag is recorded. That is a possibility. You can remove sitter tags if you're keeping a careful eye on the gear, but it's a problem. So what is rapid assessment of barriers in telemetry terms? Well, certainly it does depend on how long you need to actually sample in order to get an adequate sample of fish approaching the obstacle. If you put your gear out and no fish approach it for 2 months, then it's not going to be rapid. But if you can get a method where you can release fish downstream of it and they approach pretty quickly, then you can use it as a rapid assessment tool. And one key method for that is to use displacement of territorial fish, or fish that occupy at least a distinct home range, from upstream to downstream, some distance downstream, perhaps 100 meters or so. And then they will try and head upstream, hopefully to regain their former location. They're highly motivated normally to do so, and you can record their arrival at the barrier and the proportion of them that succeed, the time scale, the number of attempts to do so. And we've done this quite frequently, especially with brown trout in rivers. Typically between about 70 and 90% of trout that you translocate downstream of a barrier we found will try and attempt to pass it. So there's a high motivation for doing so. Not all of them will. Even though some we know are still alive further downstream, sometimes they just take up a new sort of home range. And typically it's fast. Of those that try and move back upstream, normally about 80% or more do that within a couple of days of translocation. It is quick in terms of the time that they attempt to go through. So it is possible to do rapid assessment at a single site, say a single barrier, for something like trout within about 4 days. And that includes setting up your gear, capturing a fish, tagging them, releasing them, several days monitoring, and a day of dismantling the gear. The downside is it's possible only to do that under whatever those prevailing environmental conditions are. And that's really the downside, because if the conditions happen to be very low flows, drought, then the only information on passage you'll get will be in those low flow conditions. You can also debate about how suitable this method is for species that don't show kind of typical homing behavior. If we tried to do that with something like loaches or bullheads, how likely is it that within a couple of days, a substantial proportion would have attempted to approach the obstacle? It's maybe fairly low. Some people have attempted this, but not many people have. And the answer is, we still don't really know about that. Also, you could argue about differences in motivation for species and life stages approaching barriers under natural seasonal movements and over longer periods. So, for example, we know the timing of a spawning migration, and we capture spawners way downstream, and we wait for them to arrive at the barrier. It may take us much longer to measure it. I'd argue that both approaches are valid, but the different measures. Clearly, this takes much longer, typically months, than this method, which takes a few days or a week or two. but they give you different bits of information. So this can give you quite crude information, but it can still tell you about percentages of fish moving. What about detection efficiency? Every telemetry study requires estimation of detection efficiency at each antenna. You need to use marker tags or sentinel tags to check the functionality of that gear. So with a pit tag on a stick, you can do that, or you can have a marker tag actually set in the system to keep, I don't know, send out a signal every 15 minutes, so you can check that it's still functional. Range tests under differing environmental conditions can be important as well. And where you've got multiple cross-river antennas, or you've got fish simultaneously double tagged with, say, radio tags and pit tags, or acoustic tags and pit tags, you can do these kinds of detection efficiency measures. But really, even for rapid assessments, you still need to be sure that your gear has a high detection efficiency. Otherwise, people won't believe what you're telling them, or, you know, the data won't be very valid. You've got to be able to demonstrate that. And the detection efficiency may be 0 if the antenna's broken or not working. And fish may be piling through and you would never know. How many fish to tag? That's kind of a tricky question. In many telemetry studies, sort of in the older days, a sample size might be 20 or 30 perhaps, because the tags were expensive, but you got a lot of information from each. With pit telemetry, you can tag more fish, but the problem is, until the fish arrives at the station, unless you use a mobile pit array, which is a bit like it's a little bit like electric fishing, but, or metal detecting, but with a pit scanner held in your hand and a backpack. Unless you do that in a river, you only know the fish arriving when you're running your stationary detector. So if the number that are actually arriving is a high proportion of the sample you release, then you may not need that many. So if I tagged, say, I don't know, 80 and 50 or 60 of them are detected attempting, that's probably going to be fine. You probably need over 50 to get not quite precise, simple percent passage estimates, you know, 2% increments. But if, on the other hand, only 10% of your tagged fish actually attempt passage, you might need to tag 500 of them. And you need to record the environmental conditions and the site conditions as well. I'm just going to run through a few examples here, and as befits me, I'm running out of time, but luckily we do have substantial time on this particular session, and Ian can always jump in and tell me to shut up and let's move on. But here's an example.
I don't. Just go on, Martin.
Thank you.
Still interesting.
Here's an example of how you would set up a pit telemetry system at a complex weir and fishway. So at this site, you've got the main barrier here. This is this particular weir across. The main flow of water is in this central part here, creating a large velocity flow just below it. And then people, the managers had installed 2 subsidiary, what they call pre-barrages, intended to deepen the water over a shallow bedrock plinth to give trout, in this case, water depth to jump up and over this barrier. Trouble was, it was found to be rather ineffective, especially at lower flows. And so what they did then was build this fishway, Lorinier superactive baffle fishway on the left bank here. So in this study, pit telemetry and radio telemetry was used to measure the efficiency. And we had a pit antenna, a flatbed over the shallow bedrock, pinned into the bedrock with rock eyes. And although it was a flatbed, because the river's shallow here, we got high detection efficiency, 87% during the course of the study. And then we had an entrance to the fishway here, was another pit detector, number 2, one at the top of the fishway, pit detector 3, and then one further up, pit detector 4, up here. And in that particular case, that told us the fish that passed the whole thing. We made an assumption with pit tags, if they weren't detected here or at the top, but they were detected at number 4, then they must have jumped over this structure, swum over the weir, because we had demonstrably 100% detection efficiency at the fishway entrance and exit. And we also had independent validation from the double tagged, radio tagged fish, which also told us about the efficiency of the pit telemetry. So again, that information is valuable too. We pit tagged 160 trout of 3 phenotypes. The big upstream sea trout, anadromous trout that are spawners, they've gone to sea and come back. River resident but potamodromous trout that have done their migration within the river in freshwater, but also power-marked fish. Most people would just regard those as local residents and not engaging in spawning. But a bunch of these, especially the males, become sexually mature as par, they're precocious things, and they contribute as well. And arguably, they also need to be able to migrate upstream and past these kinds of barriers. So we were tagging all 3 of those. And this figure just shows the number detected at the pit array and the first radio station, 52 out of 213. So not a particularly high number. These were all tagged at least a kilometre downstream. So some of these just never arrived. And the year we did this, the river conditions were low, and that was perhaps part of the reason. And 27 of them were sea trout, 8 of them were river run fish, potamodromous fish, and 22, so nearly half of them were power-marked fish migrating upstream. And then some of these went into the Lorinier and some of them out. Very few. That Lorinier fishway actually was poor. And you can see the small sample size here, not very good. Despite us having tagged 213 fish, we've got barely large enough samples for statistical analysis. More of these fish jumped directly over the weir, and the total detected upstream was 31. And these are the proportions of these different morphotypes. So this is a kind of just a schematic of the way you would look at the data in terms of approach, entry, and passage. And that's the bare minimum of what you actually want. This figure here just shows the cumulative proportions of the numbers moving upstream, and you can do analyses on these over time. It's a useful way to look at that data. Here's the environmental conditions. I set really low flows until the spawning season had actually started. So these fish barely got into the system and they'd already started spawning. It was almost a terrible sort of event for them. But there were some spawning areas in the main river and further downstream that they could have spawned. I said that time to passage is important as well. So here with the pit telemetry, you can see differences in the average time to passage for these groups and the time for going over the weir and the time for using the fishway. So actually the fishway was a poorer route in terms of the time it took them to locate and enter that fishway was extensive. Once they got in, they got through it without much problem, but it indicated that the attraction flow wasn't particularly good and they seemed to struggle, being anthropomorphic, to get into it and use that. Whereas the main flow went over the weir, and although it was a height barrier to some degree, fish more readily got over it. Not surprisingly, the big sea trout find it easier to get over, perhaps in terms of time taken compared to the small ones. Another quick example, doing similar things in cheap urban waterway reconnections using here low-cost baffles, wooden baffles, to slow the flow of water on a 30% slope weir, which nobody would ever recommend for cyprinid fish as them trying to get past. Here's our first antenna 1 here, 2 at the top and 3 at the exit. Here we don't have an approach antenna, which is less ideal, but we were worried about a large amount of sitter fish milling around in the pool below and give us large numbers of detections. So we decided not to do that in this case. And you can see typical proportions of passage here in terms of the fish released, intended passage through the low-cost baffles, and overall passage, so that in the order of 20 to 40% later on for a range of different species, and for stockfish and also for wild fish in this image here. So this was not high passage. We'd like 90% passage success, but it's better than no passage at all, and it's substantially better than we might have predicted would have been the case, given that this is a flow gauging weir at this site that cannot be removed. It's needed for flood defence management. And I'll try not to say too much more about this, other than I've already said, we mustn't just measure trout and eel passage, because that is not going to tell us all we need to know about reconnecting rivers for the whole fish community. We need to be able to do similar things for tiny little cyprinids like this and loaches like this at these kinds of small barriers. It's not just about a migration problem, it's a dispersal problem as well. And even if we don't use pit telemetry at fixed sites, there are ways of doing this kind of quantitative assessment to evaluate the efficacy or permeability of barriers. And here's an example where sculpins were batch marked with VIE markers and structured mark recapture done with electric fishing before and after barriers that were removed. So in 2013, this shows this site here before and after a nature-like bypass was installed. And for Bullhead, here's the orange mark, the amber mark. Oh, look, it's 0. That's good, 0 passed. Not surprising with a barrier like that. But once we put the nature-like bypass in, we're able to show that of those that attempted, 30% relatively, sorry, it's not an absolute percentage this time, but that from 0, that relative barrier permeability has increased to 0.3. So it's a dramatic increase. And the same also for North Group, young of the year trout as well. So using these kinds of methods, not just for great big trout and cyprinids and other things, but for little fish is important. If you need to know about context under which movements occur, longer term tracking can be useful. This shows movements past a barrier for these potamodromous fish, but where ultimately they're moving to spawning areas on gravels. And you only get that context and the number of attempts by long-term tracking. You won't get that from rapid assessment. And the same thing of understanding the timing of most attempts, in this case, on this river, happened when flow is decreasing, but temperature is increasing, tells us potentially some of the problems of passage because there's not enough water going over the barrier to give them as such potential to get past such a barrier. So again, if you've got short-term measurements, rapid assessments, you lose context over longer periods of time. And just also to indicate that it's not just about upstream passage, downstream is important as well, and you can use pit telemetry for assessing downstream passage of things like smolts. Here's a sea trout smolt or pre-smolt and a par here. And if we did that in 1 year here, albeit with acoustic telemetry, during low flows, there was a long delay in obstructed reaches compared to unobstructed reaches, and the next year a much smaller delay. And that difference related or correlated with dramatic reduction in its survival to getting out to the sea in this year than it did in this year. So understanding about delays, barriers to downstream migrants is important as well. Just whiz through a few examples with river lamprey. Here's some pit telemetry information on entry efficiency and passage efficiency for river lamprey at conventional fishways. So conventional for things like salmonids built in these rivers. Terrible passage efficiency, relatively high entry efficiency. We need to know that. Loads are getting in there, none are coming out. And another example on a nearby weir where a Larinio was built, the argument went from the Environment Agency technical expert that they expected this to be okay for river lamprey at this site. And so they built it. And then I asked the question here, when is a fishway a barrier for fish migration? And the answer is when the fishway is more of a barrier to migration than the barrier itself. Fishway entry efficiency is in the order of 90% here, passage efficiency less than 1%, whereas 12% of the fish got directly over the weir. So, you know, fishways can be a waste of money in some circumstances. And again, if you put your pit arrays in quite complicated arrays, so here now, 9 different pit antennas on this same weir that I just showed you, now with a hydropower plant built in since then, it shows us that large attraction to the power plant outflow, no surprise there, and also the fishway outflow, but very low attraction of fish on the side of the river for lamprey here that don't actually have the attraction of the river. And note, under conditions when the turbine isn't running and flows spread more evenly over the weir or over the width of the river, then more of the lamprey are detected immediately approaching that weir. So really useful information you can get. You can add to that with acoustic telemetry, fine scale passage, highly complex sort of bathymetry, and also information on flow patterns, which we're going to use to try and understand the fine scale paths going through there. But as it turns out, for a bunch of acoustic tagged lamprey, their paths are not highly convoluted. They pretty much run straight up the river on the left side, on the right side, and they end up here. The problem with acoustic telemetry here is that this is an acoustically blind space for us because of the noise and the entrained air. But combining that with the pit telemetry, we can tell of all these fish that were tagged through, they all turn up pretty much first detected on the pit antennas near the fish pass or the hydropower outflow, which again tells us that these fish are headed only at the very final stage to where that bulk flow is coming from. So all kinds of finer scale information you can get, but hopefully I've given you some kind of information that you can use to get you doing some very basic or rapid pit telemetry at barriers that will enable you to increase the amount of information we've got about the passageability of some of these sites, especially if you're trying to argue about the removal of a structure and you need to demonstrate the difficulty fish are having in actually passing that structure. So I've added some useful texts here that will be on the PDF. And I'll just finish by saying, concluding that actually, despite the title of this workshop, most barrier assessment with telemetry is not actually rapid. So you could say, what was the point of me showing it? But hopefully it can be shown to be informative and provide robust evidence. Okay, if we've got any time for any discussion or questions, then I'll get Ian or whoever it is, Barbara or whatever, to come up with some questions. Over to you, Ian.
Yeah, thanks a lot. That's been really, really interesting. And I'm sure the paper will be much be read by people. So let's make sure that we will distribute that afterwards. Yeah, there must have been questions, I'm sure. Sarah.
Yes, there is one question, and it is there is a question in the comments. I'll start with the question. So, sufficient number of fish for telemetry was one key sentences that you used. So, how to access that? How to access sufficient number of fish for telemetry? Is there an ideal number per species? And furthermore, studies usually have working on results with no data on how many were used. Well, there's several questions here. Let's start with the first one. How do you define the sufficient number of fish for telemetry?
Yeah, so you need to have an idea of how many fish you think will attempt or approach the barrier. And the minimum per species or life stage, I would suggest, that needs to actually approach it to give valid data is about 50. Therefore, it depends what type of behavior the fish is showing. If, for example, it is something like trout that are migrating spawning habitat that is mostly upstream of the barrier, then I think a relatively small sample size might well do, perhaps 50 to 100 adults. But if, on the other hand, you're looking at something like cottus, a sculpin, where they can, perhaps they're in habitat around the barrier where they can reproduce nearby, it may be that the only ones that will approach the barrier are those that are dispersing. And that number might be a tiny fraction of the total population. It might be that only 1 or 2 or 5% of the individuals that you tag disperse far enough to approach the barrier, in which case that sample size might need to be more like 1,000. So it's quite tricky to actually say, and it's evident that this is why most people work on migratory fishes to do this kind of thing, rather than the fishes that disperse short distances. And yet, that kind of connectivity is important for the dispersers as well as the migrators. If I was to kind of try and say what will be easiest to do, I would say pick migratory fish, like trout, but try and pick a variety of species and sizes. So pick some small, perhaps cyprinid species, as well as trout, that give a variety of gills, different types of species that perhaps show different behaviors and certainly have different ecologies. You can do that with pit telemetry, and actually tagging 1,000 fish with pit telemetry is easy. It's quite easy to do that. The costs are not too large. So don't concentrate on just 1 or 2 species. Try and pick several that you think will migrate, and usually you will end up with large enough sample sizes for some of them, and for others the sample sizes may not be so great of those that are approaching the weir, but there may be adequate information.
Okay, we have a comment that there was a link that is not working, a link to the PDF for the paper. So, but I guess then we can deal with this later. I have a question actually. It's a curiosity.
Yeah.
You said you can tag as much as 1,000 fish, and that's not difficult to do.
No.
It's 2 questions actually. Is it time consuming? And are there any studies on how does this impact the welfare of the fish, or how big need the fish to be? Because I suppose you can only do this to a certain size of fish, and therefore this also impacts on the species that you can actually use the tags. Am I correct in saying this?
Correct. So the smallest fish that can be tagged with pits are about 5 centimeters long. For the long range 23 millimeter Fdx tags that give quite a long range, maybe ½ a meter range to a pit antenna by a river barrier, the smallest of those fish that can be tagged is about 12 centimeters. So it's a 23 millimeter long tag, about 12 centimeter fish.
And do you see, I mean, there's still progress in that? I mean, is the I guess the technology is improving fast, right?
No, not that much. It improves slowly. So the smallest pit tags are 6 millimeters long, and you could tag 5 centimeter long fish with that. The problem is physics. The problem is it is difficult to get a detection range of much more than 5 to 10 centimeters for a 6 millimeter long tag or 8 millimeter tag. And so in terms of actual field studies, those kinds of ranges are not particularly effective. It means you're perhaps dealing with channels that are 2 or 3 meters wide, or pipes that are a meter wide, and you have a range of 5 centimeters. So although the technology has moved forward, actually the physics currently limit what you can do with those really small tags in terms of telemetry. So mostly we're dealing with fish that are about 9 or 10 centimeters longer or larger, and mostly the 12 millimeter tags and larger for actual field studies of barriers using in-field automated pit telemetry.
And what do you think would be the future then of, I mean, let's say in 20 years' time?
Like everything, there will probably be miniaturization, but one will probably have to increase the power field, the inductance field around the antenna in order to pick up smaller tags at a larger range. And so there's a trade-off there, that if you can have a high quality power source, and we're starting to see that with lithium-ion batteries. At the moment, most field researchers have still been using actually what we term lead acid deep cycle leisure batteries for their main power sources, often supported somewhat by photovoltaic cells to trickle charge them. But everybody's moving to high-tech lithium-ion batteries, and we may be able to get greater power sources, more maybe 18 volts or 24 volts or even higher potentially, that could generate more robust fields to interrogate smaller tags that have a weaker induction response. So to be able to detect small tags, you'll have to create a more intense induction field. And that probably will be in terms of the energy provision in for the pit readers rather than the pit tags themselves.
Right.
There's been a lot of work done as well. What Sarah was saying about the impacts of these tags on the fishes compared to traditional telemetry tags like acoustic and radio tags. These things are, the fish are tagged much more quickly, so that's less handling time, less time out of the river water, and the effects on them in most cases have been found to be minimal. In some cases, small effects on growth, temporary effects on growth have been found, but generally very little in the way of effects compared to radio tags or acoustic tags. And it's possible for a group of 3 people to tag with pit tags, to tag at least 1 fish a minute. So you could do at least 60 per hour, which means that a good team could tag perhaps, 600 fish in a day. If they've got people providing a group of 5 or 6 people capturing fish and providing them to the tagging team, you could tag 500 or 600 fish in a day.
That sounds rapid.
That is rapid. It has to be a well-trained team of people. And there have to be lots of fish available to tag.
Yes.
And sometimes in streams with barriers, the barriers mean that there may be a low density of fish available.
Yeah.
And that could be a problem. And that's perhaps one of the things that the person who asked the first question was getting at. You know, sometimes if you cannot get hold of enough fish to tag, do you try releasing stocked fish?
Yeah.
And we showed that can work. In some cases, it can work.
Okay. I have another question, if I may. May I, Arjen?
Yeah, yeah.
And also, just before I make this question, I just wanted to make a comment that from this today, for me, the highlight is realizing that we know exactly the costs, and the costs are not as great as I thought there would be to make these things. And the timing, I'm fascinated that we can tag this amount of fish. And then from the previous session, I was fascinated to learn that it doesn't take that much time to model and to do the fieldwork. So this is just a comment. So to the next question is, how about camera recognition? Instead of using telemetry, I suppose, how about going using camera recognition? I actually have colleagues who've done this with in marine environments.
Yep, so it can be used in the field, and of course, automated individual recognition, pattern recognition is moving forward fast. You know, it's used all the time for things like, I don't know, mammals, for example, whales and stuff. But to do it on an automated base in real time, that is still really, really tricky. And actually, one needs clear water to do it. And often in rivers, you've got a large amount of entrained air near barriers, and you've got a large amount, in some cases, of fine sediment. So it would only be able to be used in very specific circumstances and over short distances. And it has to be built in with a big database of individually recognizable individuals. Because, for example, European grayling and Eurasian pike can all be recognized from individually from their individual body markings, but that's usually done in a laboratory environment,
Right,
you know,
right.
taking pictures and bringing back. Translating that to real-time analysis would be tricky. And you could record vast amounts of records and then try and trawl through them later on. Maybe something to watch for the future.
Yeah. Yeah. Sarah, one more question and then we will close.
Okay. So the last question then, how about taking fish from above barrier, tagging them and releasing them under barrier to access passability?
Yeah, that's what I said. That is the main rapid assessment tool.
Yes,
you take the fish from upstream and you translocate them downstream of your furthest downstream pit antenna. So the fish has got to move, say, at least 100 meters upstream before it's detected, and that itself is some way downstream of the actual barrier. So you pick up the full approach series of events: approach, enter, pass, and exit out at the top or the bottom if it's the other way around. But there will probably be some species that method does not work for, and we need to do a lot more work on that. So at the moment, the main species people have used to try and do that are a range of cyprinid species, a range of salmonid species, and perhaps one or two others as well. But more work needed there.
Okay. All right. Thank you very much. This has been very engaging for 1.5 hour. Compliments to do that. And it's not the first time that you do such a talk, I notice, and it's really appreciated. Thank you very much. I would like to say, it was an issue which has been mentioned quite a lot also during the talk of Martin, when weirs or dams are removed. At the moment, there is a dam removal going on in the UK, and we have been asked to tell that to you. Maybe it's possible, Bas, to show it for a minute as well. It's a live broadcasting of a dam removal, just for fun, just to have a little look, which is going on in the UK at the moment. I'm not sure, Bas, if you can show it right now. This is happening right now. It's such a shame. I've been talking to Martin about this before we were starting. It's such a shame that they did not do telemetry at this place before and after the dam removal. And I think that's something we really should think of in future. We have more moments where we do telemetry in advance of dam removal or dam mitigation projects and afterwards. And I think Martin has shown how that's possible, how we can work towards that. It does not have to be too expensive, but it certainly is something to do more in Europe in future. So what we see here now, Martin, do you recognize which river this is again?
No, but I think it's in the northwest of England.
I think you are right. The Harrowby Weir. So they're currently taking this out. And anyway, if people want to continue watching this, I think the link has been shared via the chat. So you can copy and paste there. And meanwhile, we will continue with closing down our session on the way that we do that in the summer camp by asking Cesar Rodriguez to play a campfire song for us. Again, Martin, thank you very much for your presentation. Thank you everybody for watching. And we hope to see you again tomorrow morning at 10 o'clock, where we'll be talking about the barrier tracker and the future of a barrier tracker. Will we going towards professional use, or will we going towards more citizen use? And we are also interested what you in Europe think about that. So, thank you very much. Cesar, are you ready to play a song? Thank you, Martin. Cesar, maybe I need to give you a little warning or a call. And Bas, don't you think it's time to start the campfire? Yes, there we go. Or, now that I think of it, Bas, maybe we should play the video of the dam removal at the moment. How about that one? Meanwhile, I'll try to get hold of Cesar. No, I'm sorry, I can't get hold of Cesar, but with this view of this dam removal, I hope you enjoyed this session as well, and hope to see you tomorrow. So let's close down the session now. Thank you very much. And I'll just read that Martin says, copy of the talk will be made available to everyone. Great, and also the paper. Fantastic. All right, thank you. Bas?